So we were talking last time about the probability transition matrix. And now the thing is, there's a couple of matrices in this family, but they more or less all have the same form. That being said, I do want to switch gears and talk about a different matrix. And so today's matrix will be the normalized Laplacian. And the way that we're going to define it is as follows. So the normalized Laplacian, we'll define it entry-wise. It is 1, and I should put some uv here. So 1, if u equals v, not isolated. And we'll come back to why we specify that in a second. Minus 1 over the square root degree u times the degree v, if u is adjacent to v, and 0 else. All right, so those are the three types of entries. You're either 1 on the diagonal, unless for some strange reason you're an isolated vertex, and in that case you're 0. And then if you're a non-edge, you're a 0. If you're an edge, you're minus 1 over square root degree u degree v. Okay. Now, for all intents and purposes, we don't really care about isolated vertices. There's a reason why we like this variation. So most of the time, when you read papers, no one's going to point out this subtlety, and they'll just say, well, the normalized Laplacian is written as d to the minus 1/2 L d to the minus 1/2. And it's true. This is absolutely true as long as there's no isolated vertices. But the question, of course, when you get isolated vertices, how do you handle 0 to the negative 1/2? And so that's why you have to be a little bit careful in your definitions here. All right, so that's our normalized Laplacian. Well, what can we say? This is also, if we follow this, this is the identity matrix minus d to the minus 1/2 a d to the minus 1/2, because the Laplacian is d minus a. And you just say, well, okay, d to the minus 1/2 times d to the minus 1/2 is the identity. And it raises the question that you might say, okay, so it looks like there's a connection to the Laplacian, and it looks like there's a connection to the adjacency. And so one question is, does L behave more like the Laplacian matrix or more like the adjacency matrix? And okay, well, all right, that's a question one could ask. And the answer is kind of. It just sort of depends on context, what it is you're trying to measure. So there are certain things that you can capture with the Laplacian, and now I have to be careful. I will try to say normalized Laplacian consistently, and when I don't specify Laplacian, we'll assume that I mean our old school Laplacian, sometimes called the combinatorial Laplacian. And okay, so there are things that the Laplacian is good at, that the normalized Laplacian also is good at. But there are things which A is good at, which the normalized Laplacian is good at. And so we have these sort of interesting things. And of course, there are things that they're both L and A are good at, but that the normalized Laplacian is bad at. I do have to say this is not really having nothing to do with spectral graph theory, but oftentimes in the back of my mind, when I see this fancy L, I think about LaTeX, and it's math cal, so I think Cal L, like it's like the Superman of matrices. Yes. All right. At least one person knows the reference. Okay, good. All right. Good. Now we've. I won't try to explain it to young people. You just won't
Thanks.
get it.
Thank you.
So.
Now I kind of want you to explain it.
Kal-El.
I know what
So, all right. Okay. So, what are some nice facts about our normalized Laplacian? So, okay, things that we can say. Well, what's the multiplicity of 0? What does that tell us? What do you think it should tell us?
It should tell us the number of connected components to it.
Yes.
Because L is two invertible. To get to the normalized Laplacian, you have to multiply L by two invertible matrices, so it won't affect those eigenvalues or your.
Well, of course, you're looking at this definition.
Yes.
But you also have to say, if you even go back to the older definition, so if we say, okay, there are no isolated vertices, things are a lot easier to see. So one of the things you can say is, think of the probability transition matrix. You can say, what would an eigenvalue for 0 for the normalized Laplacian correspond to in terms of the probability transition matrix? Now, roughly speaking, this is not quite true, but roughly speaking, this is similar to I minus D inverse A. So it's behaving like I minus the probability transition matrix. So in terms of the eigenvalues. So an eigenvalue of 0 for your normalized Laplacian corresponds to an eigenvalue of what for the probability transition matrix? The answer is 1. Okay, good. All right. And so, okay, well, but how many times do you have an eigenvalue of 1 for the probability transition matrix? Again, we're going to assume no isolated components. There's actually a great question. What does it mean if you have isolated vertices and a random walk? Well, you might say, that just means you're stuck there. Well, it's worse than that. It's just, you can't even move. Things break apart. So anyways, so the punchline is that for each component, you get an eigenvalue of 1 in the probability transition matrix. And so we say, aha, multiplicity of 0 is the number of components. Now, let's actually step back here. We said a few things about the probability transition matrix. We said that the eigenvalues are, because we pulled out our sledgehammer, we don't actually have to pull out our sledgehammers to prove this, but they're between -1 and +1. Because we found an eigenvector, which was positive for the eigenvalue of 1, and that's therefore had to be the largest in magnitude. So the eigenvalues are between -1 and +1. So the eigenvalues of the Laplacian matrix will be between what and what?
2 and 0.
Yeah. So eigenvalues are between, and we'll put them as 0 and 2. So there's a nice interval here. So at one extreme, we get the number of components. And this, by the way, is why for isolated vertices, we like to put 0 on the diagonal. Because then what happens is that says, okay, you get 0 as an eigenvalue, and that says I'm picking up that isolated vertex as a component. All right. So how about multiplicity of 2? The other extreme, because our eigenvalues are between 0 and 2, what can we say about the multiplicity of 2? Well, think about, that would say that for your probability transition matrix, it's the same thing as asking multiplicity of -1. How can you get an eigenvalue of -1? Pull out your sledgehammer. Perron Frobenius. It has to be bipartite. If it's not bipartite, think of it just as go component by component. So for each component, the largest eigenvalue will be +1 in the probability transition matrix. We're connected because we're a component. So we only have to check, are we aperiodic, which means are we bipartite or not bipartite. So if we're not bipartite, then our other eigenvalues are strictly between -1 and +1. If we are bipartite, well, that means that we're periodic. We're sort of jumping back and forth between the two sides. And so in that case, we have symmetry. And so that says we get an eigenvalue of -1. 1, eigenvalue -1 for each bipartite component. So the multiplicity of 2, that's the number of bipartite components. All right, well, that's cool. So it's like we can detect things that the Laplacian matrix detects. We can detect things that the signless Laplacian matrix detects. All right, here's a question. And just to simplify our discussion, in this question, let's assume there's no isolated vertices. It doesn't matter. It's just a more subtle discussion. So question, can you detect bipartite? So we'll assume no isolated vertices when you're answering this question.
If it has a 2 for an eigenvalue?
Well, if it has 2 as an eigenvalue, the thing you can conclude is that some component is bipartite. So the question is, how do you know if your whole graph is bipartite?
The number of bipartite components is the number of components.
Yeah, you just check. How many components do I have? How many of them are bipartite? If those numbers match, then it must be that the whole graph is bipartite. Now, spoiler alert, you never have more 2s than 0s. So you can't have more bipartite components than you have components. So the answer for this is yes. Check above numbers. Okay, great. So now, this is good because this is something that the adjacency matrix can detect. Now you might think, okay, that's very specific of you, Steve. Let's do one more thing. Okay, so one more question. Can you detect the number of edges? Now this is hard because we actually we don't know many spectrums. So, excuse me, let's see if we can do some easy spectrums. What are some good spectrums? Well, we know complete graph, okay. Complete graph though is pretty extreme. Let's take a look at complete bipartite graphs. Let's try that. Can we detect the number of edges? Well, okay, so what is that? That's the graph K, P, Q. Okay, so our goal is to figure out what's the spectrum of this graph. Now we can find it for the probability transition matrix, or we can find it for the normalized Laplacian. There's lots of things we can do. Do you have a preference where to begin. Well, let's try this on size. D to the minus 1/2 A, D to the minus 1/2. Now, for the adjacency matrix, a complete bipartite graph is very straightforward. You have zeros and you have all ones pieces. And then what's going to happen here is we're going to scale. And this is the part that's always going to throw me off for a second here. So I just have to, okay, let's say there's P vertices here and Q vertices here, P vertices here, Q vertices here. So when we look at D to the minus 1/2, A, D to the minus 1/2. And I am making no claim that this is the best way to go about solving this. So I just want, no one should come and say like, oh, Steve, you chose such a terrible way to solve this. And I will be like, yes, I did, and I apologize for it. So, all right. So, if initially, so I'm in the smaller side, on the side with P vertices, what's the degree in KPQ? It's degree Q, yeah. So this is 1 over square root of Q, down to 1 over square root of Q. Switches to 1 over square root of P on the other side, 1 over square root of P. All right, then we have our block here. And to the, yeah, no, this is good. That's D to the minus 1/2. And same thing over here. All right, cool. Well, what do we need?
You want eigenvector?
Sure, I love an eigenvector. Do you have an eigenvector? Later on, we're going to be like, oh yeah, we could have just done that. Don't be fancy. Don't try to make a complicated eigenvector when a simple eigenvector is available. Yes. Yes. If we covered these parts up and said, what's an eigenvector for that look like? Just for the bipartite graphs. Again, there's complicated ones. Go for simple ones.
All ones vector would work. If you cover that.
Well, that ones wouldn't quite work. You'd have to scale the different parts appropriately.
What if it's 0 and then 1s?
That,
Like some zeros, not just 1 0.
well, I think you have to be careful because we can kind of pull out our sledgehammer and say there's going to be issues with that vector.
Okay.
Because we know that we have an all positive eigenvector because it's connected. And so everything has to be perpendicular to that. And so every other eigenvector has to have at least one negative.
Okay.
But maybe one is enough. One negative. And maybe one positive.
A 1 and a minus 1.
Yeah, let's try like a 1 and a minus 1, right? Let's just go ahead and be very simple. We'll do it just near the top initially. What would happen? Well, you'd have a 1 over root q, and a minus 1 over root q, and the rest would be zeros. And then when you multiply here what happens is you sum those. It doesn't matter that it's 1 and minus 1 versus 1 over root q and minus 1 over root q. You're going to get 0. And then as soon as you're 0, it doesn't matter the next step. So you'll still be 0. So you say, oh, well, that's a nice eigenvector. It's an eigenvector that corresponds to 0. All right. Well, how many of those do we have? Do you agree with me that that works? Yeah, I feel there's some skepticism. It's okay to be skeptical. I'm trying to squeeze too much into this little tiny sliver of page here. But essentially it's just plus a number minus a number. And then when you multiply across, well, you get 0 times that first number, 0 times minus that number, and then everything else is times by 0. Then here you get number minus a number, everything else is 0. So it's always 0 all the way down. So how many such eigenvectors do we get?
I feel like it should be P choose 2 plus Q choose 2.
Aha, that's a great answer. Now, you say you feel like that. Is that the right answer?
The way you said that makes me think no, but there might, like, I think that's a good basis to start for finding them.
Oh, interesting that you said that's a good basis to start. So it is true that all of those work as eigenvectors, but there's some redundancy built into if you use all of them. But if you fix, say, the top one and let the minus 1 move around, and then go to the bottom half, fix the top one, let the minus 1 move around, then you will get p plus q minus 2 such eigenvectors that are all linearly independent.
Does that kind of thing always work for determining multiplicities?
Well, what we're really taking advantage of is that we have twin structures, and twin structures work really great. And so when I say you have twins, you have two vertices which have the same neighborhoods. And then if you just think about what it means in terms of matrix multiplication, whenever you have a twin, regardless of what kind of matrix you're dealing with, unless it's a really terrible matrix, you'll essentially will get an easy eigenvector by saying make one twin a plus 1, make another twin a minus 1, and then just like figure out what happens. And so here it's like we're overflowing with twins. And so that helps us just get tons and tons of eigenvalues because we get tons and tons of eigenvectors. We're not done. We've only found p plus q minus 2 eigenvectors. So that means we've only found p plus 2, q minus 2, eigenvalues. So there's still 2 eigenvalues that we don't know. But what are they? Well, essentially we're doing the probability transition matrix. So what do we know about, for a bipartite graph, for a probability transition matrix connected, what eigenvalue should it have? Should have 1 and minus 1. And so another thing we can say, we'll put it down here as a fact. So for the normalized Laplacian, the graph KPQ has eigenvalues. So this is for, I just want to be clear, I don't want to make it sound like I'm cheating. This is for probability transition matrix, so you have to do your shift. So the way you do your shift is you negate your eigenvalues, and then that's what the minus does, and then you add 1 to the eigenvalues. So the result is you get 0 with multiplicity 1. You get 1 with multiplicity p plus q minus 2. And then you get 2 with multiplicity 1. So those are your eigenvalues for KPQ. Okay, so back to the question. Can you detect number of edges? Given that we just found this, this should probably be a strong indicator of where I'm trying to get you to. So keep in mind that a yes answer requires a proof that you can. A no answer requires an example that you can. So oftentimes we prefer no answers because they're short. So can you detect the number of edges using the normalized Laplacian?
Probably not.
Probably not. Okay, do you have an example for us that helps us say, you are correct. Here is an example. If only we had some graphs which we could easily compute the eigenvalues for, and somehow they were different, that we could say, clearly these graphs are not the same number of edges, but also must have the same number of eigenvalues. If only there were such a thing available to us. If only we lived in such a world. What a world, what a world.
Okay, well, one of them is going to be complete bipartite.
Okay, one of them can be complete bipartite, and what can the other one be?
Complete.
Also complete bipartite, because there's multiple complete bipartite graphs. So, what's an example then? What's our first complete bipartite graph?
Oh, using 5, 5.
Can we go a little bit smaller so we can actually convince ourselves?
3, 3.
How about 1, 3?
That's fine. And K2, 2.
And K2, 2. Now, first off, let's convince ourselves these two don't have the same number of edges. Okay, I'm convinced. 3 versus 4. All right, easy to count. That's why I want to keep it small, so I don't have to count for very long. Do they have the same eigenvalues?
1 plus 3 equals 2 plus 2.
Yeah. So they both have the same. Since the p plus q is equal in both, then we get they both have an eigenvalue of 0 with multiplicity 1. They both have eigenvalue of 1 with multiplicity 2, and they both have eigenvalue 2 with multiplicity 1. So 0, 1, 1, 2. And so this shows you can't detect the number of edges. So you're really good at detecting certain things about the graphs, but then you're like, the most simple thing you'd want to count, the first thing you'd want to know about a graph, how many edges do you have? And you fail. And I don't just want to say you fail. You fail spectacularly. And what I mean by that is that, so K13 is a star. So you can look at a star. And that's very few number of edges. Indeed, a star is a tree, and that's essentially as few edges as you can have and still be connected. So we would consider it very sparse. On the other hand, you can look at something like k n over 2 n over 2. How many edges does that have? Yeah, n squared over 4, you're right. You multiply the two sides together. That says that there's only n squared over 2 edges, okay, and with lower order terms, but that says you have half the edges. So that's like a super dense graph. So you can have a sparse graph have the same set of eigenvalues as a dense graph. And so you really have no clue. But it turns out you can even have wilder things. With a graduate student, we came up with an example where you have two graphs. One is a subgraph of the other graph. One of them is sparse. It's essentially unicyclic. And the other one is dense. It has order n squared edges. And so you can't make any conclusions in general. So, all right. Also, there's other things that you lose. And we haven't proven this yet. But it turns out that for the adjacency matrix, the Laplacian matrix, signless Laplacian, you can always tell if a graph is regular. There's ways to do that. what about for the normalized Laplacian? Can you tell if a graph is regular? Okay, someone's saying no. All right. Do you have an example for us? Yeah. Same example. K13 versus K22. Not regular, regular. All right. Well, I feel it's good to sort of help us remind ourselves, okay, that all these matrices we've talked about up to this point, they are indeed all different. They all have their own strengths. They all have their own weaknesses. So I like the following table. So I'm going to write down the 4 main matrices we've talked about. We've talked about the adjacency matrix, the Laplacian, the signless Laplacian, and the normalized Laplacian. All right. And we're going to make a little chart here. And we're going to ask ourselves questions. Can you tell if BIP here stands for bipartite? Can you tell if you're bipartite or not? All right. Can you tell the number of components that you have? Can you tell how many bipartite components you have? And then in the last column, can you say how many edges you have? All right. So for the adjacency matrix, these are yes/no questions. Either you can or you can't. Can we tell if we're bipartite from the spectrum of the adjacency? Yes or no?
Yes.
Yes, we can. How do we do it?
If we can make it the 0 log in the upper left and bottom right and not the other.
Well, that's if we were bipartite. That's definitely how we can do it. But looking at the eigenvalues, that's my question. Looking at just the eigenvalues, what is it we're looking for? Symmetric, yes. Symmetry around 0, we're bipartite. Can you tell how many components you have? And while you think about that, I'll casually just draw a graph.
No.
You cannot. Yes, so this is called the Saltier pair. And the reason it's called the Saltier pair is if you cross your eyes, it looks like a square with an X through the middle, which it looks like something called the Saltier flag. Okay, so you cannot tell how many components you have. Well, that's disappointing. Can you tell how many bipartite components you have? No, because you'll see here there's 2 bipartite components, 1 bipartite component. Can you tell how many edges you have? Yes. Good. Okay, so Laplacian. Can you tell if you're bipartite? All right. Now that one might be a little bit more subtle. So again, I'll just randomly be drawing while you think about the answer to that question. And who knows what these scratches mean, but. So this is the smallest pair of cospectral bipartite graphs for all intents and purposes. So can you tell if a graph is bipartite from looking at your Laplacian eigenvalues? No. How do we know? Because there's an example. These are cospectral for the Laplacian matrix. The one on the left is bipartite. The one on the right is not. So okay, well that's disappointing. How about how many components you have? Yeah, that's the multiplicity of 0. Okay, how about number of bipartite components? Can you tell how many bipartite components that you have from the Laplacian spectrum? Now, of course, we haven't proved it in class. That doesn't mean that you can't, unless, of course, we had an example. Is there an example where somehow we have things which are co-spectral, but they have different number of bipartite components? Yeah, this is an example. This one has one bipartite component. This has 0 bipartite components, but they're co-spectral. Now, you might say, I'm skeptical about their co-spectral. That's okay. It's fair to be skeptical. And you can go and compute the characteristic polynomial, and you'll find out that they are indeed. How about number of edges?
Yes.
Yes. Okay, cool. Okay, now we're up to signless Laplacian. Can you tell if your graph is bipartite from looking at your eigenvalues? Just randomly, I'll be drawing some pictures here. As a comment, these are the smallest pair of co-spectral graphs for the signless Laplacian. Yeah, no. See, one on the left is definitely not bipartite because there's a triangle, and the one on the right is a star, which, all right, so that's a no. Can you tell how many components you have? No. This has 2 components. This has 1 component. Can you tell how many components are bipartite?
Those two are the same.
If you can't tell us bipartite, then you can't tell how many components are bipartite.
Are you sure about that?
Because if you have 1 component,
Oh.
Evidence says yes.
Sorry, what?
Evidence says yes.
Okay. The one example says yes, all right. We'll channel our inner physicist and say it's a yes. It is actually a yes. And so what happens for the signless Laplacian, it's multiplicity of 0 for the signless Laplacian is the number of bipartite components. And that's because for bipartite components, the spectrum isn't affected. If you're not bipartite, though, your spectrum is changed and your lowest eigenvalue moves away from 0. Can you tell how many edges you have?
yeah.
Yeah, it's basically the same way as you do it for the Laplacian. You just add up the eigenvalues. That's the trace, which is the sum of degrees. Okay, now for the Laplacian, this is, while these other matrices were reviews from way back when, this is from today. So I'm hoping this will be a faster conversation. Okay, can we say if the graph is bipartite?
Yes.
Yes. Can we say how many components it has?
Yes.
Yes. Can we say how many components are bipartite?
Yes.
Yes. Can we say how many edges there are? No. All right. Now, what's the punchline here? Well, the punchline is that each matrix is different. But, okay, so you've already spotted another pattern. Namely, if you mark where we get the yeses, so we'll do that here just to highlight. It is indeed symmetric. And so that tells us that there's something real going on here. So that's the moral of spectral graph there. We've got something real here. So yep, that's our meta result. And all right, good. And you anticipated. We have just a few minutes left. I do want to mention one thing that we'll get into in a little bit next time. So we have our Laplacian matrix. So that's d to the minus 1/2 L d to the minus 1/2. And when we worked with, in the past, we've talked about eigenvectors. We want to sort of spice things up or change things around. And so we're going to move to, instead of an eigenvector, we want to move to what are called harmonic eigenvectors. And I have to be very careful here about what I'm going to say because I want to make sure I get this right. Because it's easy for me to making mistakes. I'm checking my notes here. I know you're like, wow, Steve actually brought notes today, so he's actually trying. Yes. Okay. All right. So the idea is if we call our eigenvector x, and so we know what it means to be an eigenvector. It's just, the harmonic eigenvector is d to the minus 1/2 times x. Okay. So essentially, it's just you're taking your eigenvector and you're scaling it by this d to the minus 1/2 term. All right, now, at first glance, it seems like, why would you do that? And let's see if we can quickly run through things that happen, which are nice. So, we are looking at this d to the minus 1/2 L, d to the minus 1/2 x. And our goal is to say, well, this is equal to lambda x. Because we're an eigenvector, so there's an eigenvalue. All right. Well, what can we say? Well, d to the minus 1/2 x, what's that? Well, yeah, I'm asking the questions. Oh, wait, oh, you mean y as the vector? Yes. All right, good. Okay, so this is the y term. And now, what we'll do is we're going to take this d to the minus 1/2, and we'll move it to the other side, because it will make it a little bit easier for us to play with. So we have L times this y is equal to, well, lambda is a scalar, so it can just push through, d to the 1/2 times x. Now, what would we like to have over here? We like y again. What's the problem? Yeah, we need minus 1/2. This is positive 1/2. So what do? Well, we make it minus 1/2 x. But if we make it minus 1/2, what do we need to add? We have to add d. So this is lambda dy. And so what's happening is that for the harmonic eigenvector satisfies Ly equals lambda dy. Now, let's see, how much time do we have left? Oh, we have no time left. Okay, so next time we're going to say, how does this translate at an individual vertex? And we're going to be like, oh, that's kind of cool. Maybe we can make the square roots kind of get hidden away. So the whole point of harmonic eigenvectors is we're going to see, oh, you can kind of sweep the square roots under the rug. And then it feels like, okay, I'm more comfortable without any square roots. So that's next time.